So I'll start the recording once again and welcome you to the network basics for cloud computing. And in this chapter, we want to understand why is it important for us to look at some of these network basics and how do they even apply when it comes to cloud computing. Previously, in the previous chapters, we understood, I think in the introductory chapter, we understood that cloud computing is built on virtualization. And also we came to appreciate that one of the characteristics of cloud computing, or for us to be able to use cloud computing, we deeply rely on the network. And of course, some underlying technologies like virtualization. So today, network consists of various types of network devices, like you have told me, routers, switches, etc, etc, etc. And for us to be able to, to have meaningful communication, like let's say from computer point A to computer point B, we shall need some kind of physical network equipment to use. Maybe we shall have our switch here, in between here, which is going to be, sending our packets, and we shall need to connect our computer with a physical cable to that switch, and then we also connect this computer to that switch, and then we are able to have some kind of meaningful communication. Even this switch, maybe we shall need to either connect it to our router, which our router will also maybe connect using a fiber or radio, whatever communication, to our internet service provider, and then our computers are able to have access to the internet. So with the cloud computing, many network devices are virtual entities, and these entities just run inside servers. I know it sounds a bit odd, like for them they are virtual, they're actually not physical, and these virtual devices communicate with each other not directly through a network cable or through these things you have seen me drawing on the screen, but through entries in some kind of logical forwarding table, which possesses also new challenges to network administrators. Because if you're going to be a network administrator and the kind of network you're administering also has virtual machines and virtualization and cloud computing, then you also need to make yourself well aware of such things that happen. So that's why this chapter we are going to describe some of the physical and virtual devices that are used in cloud computing. So moving forward, the network, like we have said, it consists of a variety of devices. And in addition to the traditional physical network, the network for a virtualized environment also includes visible networks running inside our servers. And in this chapter, we will focus, we'll cover the basic knowledge about both types of networks. Upon completion of this course, we shall be able to understand how physical and virtual switches work. We'll also understand the network architecture used for virtualized environments. We also understand the traffic flows between virtual machines and also understand the concepts related to the virtual area, local area network, the VLAN. So let us look at some of the network architecture for virtualization. How do virtual machines communicate? Remember, we said we have our let me see if I can get a box here. I don't think I can get a box. We have our physical server. This is our physical server, and we're going to go ahead on our physical server and we're going to install our hypervisor. And inside our hypervisor, it's going to help us to manage our virtual pool of resources. And we're going to create our virtual machine A, we're going to create our virtual machine B, virtual machine C, and maybe also virtual machine D. This is B, this is C, this is A. So how are these virtual machines, how are these VMs going to be able to communicate with each other? Because we said for machines to be able to communicate in a traditional IT environment, we need some kind of networking equipment that even work at different layers. For example, the switch works at layer 2 and our routers work at layer 3. So how are these guys going to be able to communicate? Yet this is just a server somewhere in our computer. How are these virtual machines going to be able to communicate? And in this course, maybe I also would love to ask you guys, how do you think virtual machines communicate? Anyone can tell me what they think? How do they communicate with each other? Yes, Prosper, your hand is up.
I think they would have to communicate via virtual network interface cards.
He says
Thank you.
via virtual network interface cards. Okay. Anyone else?
Sorry, can I speak?
Yes, yes,
Uh,
Sadula.
Eh, Yeah, according to me, I think so. They are just want to communicate uh, due to their virtual instance.
Virtual instance.
Yes.
Okay, yes, Isaac Nambafu. I hope I'm
uh,
pronouncing your name correctly.
yeah. Good evening, guys.
Good evening.
Virtual machines. You remember the virtual machine monitor is the one used to control allocation of resources. Now, once you install the operating system and whatsoever, we have things like uh, you're provided with a bridge adapter or a network address translator. Now, using those, and of course, if there's some form of network, the virtual machines are able to communicate.
Okay, thank you. He has talked about those things. And lastly, Lugemwa, and then we move forward. Thank you.
I give a contribution.
Let me first take on
Virtual
Lugemwa, then you can come
machines.
in.
Thank you. Virtual machines. I think virtual machines communicate through the host. Thank you.
They communicate through the host. Uh,
Okay, I can give another contribution just to add on.
yes, Jason.
Okay, so since virtual machines are a simulation of the reality to some context, so you'll find out that as they use the physical resources that have been allocated to them, for the network aspect of it, the virtual machine will utilize the hardware and then simulate that the allocated amount of same resource. So in some context, they just simulate the physical network connection between different systems.
Okay, thank you. And Manza, you have some quacking noise in the background. Please mute. Manza. Okay, thank you all for contributing. So now we want to try, and before we even get to how virtual machines communicate, let us look at we have our different scenarios and how virtual machines communicate, and want to look at some of the traffic that is generated when virtual machines communicate, all in a virtualized environment. So we want to look at the architecture for virtualization. In cloud or virtualized based environments, traffic can be divided into two. There's what we call north to south traffic, and there's also what we call east to west traffic. And I want you to pay attention to this. In our traditional IT systems, we do not make such distinctions. Actually, we even don't pay attention to that kind of north and south, west, east traffic. But because we're in a virtualized environment, now we need to pay attention to this kind of traffic. And for us to determine that this is either north to south or east to west traffic, we can determine this traffic by using a router which acts as the demarcation point, or objects, which acts as a demarcation point between the north and south traffic, or how the device that we can use to differentiate between east and west traffic. So what I'm trying to say here is that any kind of traffic that is going to traverse through a router is a traffic we are going to call north-south traffic. Any traffic that is going to traverse through a layer 3 device, or that is going to be routed, is what we are calling a north to south device. So generally, the our router acts as a demarcation point distinguishing north to south traffic from east to west traffic. The router can either be physical, okay, or it can be a virtual one inside a virtual machine. So traffic that passes through a router is what we're calling north to south traffic, while traffic that does not pass through a router is what we are calling east to west traffic. So let's say we have a virtual machine here and he wants to communicate, send out packets to, let's say, an access Huawei pages somewhere in the cloud, and you are using a virtual machine here. So this traffic that is going to come from this virtual machine and go through here and go through there and then come here and go through the router, this is what we are calling north-south traffic, or even any traffic that is going to come and come back here and go through, and come back is what we're calling north-south traffic. But then in case we have, let's say this is our physical application layer, right? This is our physical application layer. And let's say this is our database layer. This is our database server, right? And our application servers here want to access files from our database server. And there's traffic that is going to be generated from this server here that is going to go all the way to within our internet data center, within our data center. And this traffic, which is going to be traversing here between these, between these virtual machines or machines, is what we are calling east to west traffic. I hope that is clear. I hope that is clear. So before we also get into, all those other details, I also want us to, try and understand some of the different modes or ways we can have different virtual machines. As you can see here in scenario 1, we can have a virtual machine. It has its virtual network interface card, which is directly connecting to the network interface card of our physical server A1 here. And it's directly connecting. We have another scenario here. We have our virtual machine here. This is virtual machine 1. This is virtual machine 2. We have virtual machine 2 here, which has its VNIC, and it is connected to some kind of virtual switch. Are you seeing this? To some kind of virtual switch, which is inside our physical server. This is a machine, like a physical server, right? So we have some kind of virtual machine, and we have some kind of switch inside where our virtual machine is connected to. And this virtual switch now can go ahead and connect to our physical NIC of our physical server. That is scenario number 2. We have here our virtual machine 3 here, and we have our virtual machine 4 here. We can see in this illustration here that virtual machine 3 and 4 all can connect to the same virtual switch. Is that making sense? Which virtual switch now can connect to our network interface card of our PC, physical PC? This is a PC, right? Of our physical server, and then now they can be able to access our network. Now we have our scenario 3, and we have our virtual machine 5 and virtual machine 6. With virtual machine 5, you can see it can be connected. It is within the same physical server with virtual machine 6, but you can see it can be connected to its own virtual switch. The same also applies to virtual machine 6, and also is connected to its own virtual switch. And then this virtual switches now also connect to our physical network interface card, and then boom, they are connected to our network. As you can see here, virtual machine 7 and 8, there's a difference here on this virtual switch. Let me call it Z. On virtual switch Z, as you can see, it is this scenario here. It is this scenario here, where you can have more than one virtual machine connecting to one virtual switch. Okay? As you can also see, this virtual machine connecting to its own switch here, it is already this scenario, all this scenario here, where you can see you have one virtual machine connecting to its own virtual switch. So there are some of the different scenarios that we can have that our virtual machines can be able to access and connect to our network. So we have talked about east and west traffic. Just to confirm again, I told you east and west traffic is generated when our traffic traverses through a router. North and south traffic is generated when our traffic traverses through a router, and also east and west traffic is generated when our traffic, is just moving across our data center. So this is what we would call east-west traffic. It is going to just traverse east-west traffic. It's going to just traverse through our data center, and the traffic that is going to move, and it is moved through a layer 3 device or our router, is what we are calling north to south traffic. So moving forward, the basic concepts of network concepts. Some of these things, I am happy to note that some of you guys have been part of have been part of my previous classes. Today in the morning, we also looked at networking. I think we're having a security class. We also were dealing with some bit of I think we looked at it the other time. But we have some of these concepts, basic network concepts. Broadcast, unicast. There's another concept called multicast, right? And I'm not going to speak a lot. When it comes to unicast, we are sending packets to how many hosts on the network?
One.
Okay, we are sending to only one. When we say multicast, we are sending packets to how many hosts on the network?
Multiple ones.
A selected
Many
group
but
of,
known.
just a selected
Many.
group.
Yes, many that are known. That is also key. Thank you for that. Many that are known. When it comes to broadcasts, what are we looking at? Where are we sending our packets?
Like all hosts.
Okay,
Public.
thank you. So we are sending all hosts on our network. So that is broadcast and unicast. Now there's also something that they are calling here our default gateway and route. We're going to be looking at them. I'll just give you an example for you guys to think about it. Yeah, default gateway. We said that computers communicate usually to all the computers that are within the same network segment, isn't it? Within the same area. But what happens now if this computer wants to communicate to another computer, which is not in its network segment, but it wants to communicate to that other computer? How is it going to be able to tell that, you know what, I need to reach out to this computer? Just like we have our friends, some of them are from Zambia, some are from Tanzania, some are from Uganda, and now we want to reach each other. Think of it, the default gateway, like our country codes. To make it easy for us to call people in outside countries, we have our international default codes. I know if I want to call my colleague in Kenya, I don't have to bother the net telecom communications. I just need to, first put their default gateway and I say, this phone call is meant to go to Kenya. +254 goes to Kenya, and then I'll go ahead and put their other numbers. So when I dial my number and I start calling, the packets are not going to first route through all the telecom masts. They go to MTN, they go to Airtel, they go within Uganda. No, it will directly be routed to the network of Kenya because I know I'm calling someone from Kenya. And if this someone wanted to call me in Uganda, he will say +256, okay? And then they know. Or let's say you want to call someone, even the telecom companies have their own, gateway numbers. So whenever the dialer sees that number, they know I'm either calling Airtel or MTN. Depending on your country, they have different codes, right? So think of it that way. Imagine if that was not there and just dial a number and we don't know if we can reach that number from Kenya or Dubai, and they have to first go throughout the entire world to find your number. Wouldn't it take like 1,000,000 years waiting until you get a response, until someone's phone starts ringing? So think of the default gateway in that way. The default gateway basically works like the default route, okay? Just works like the default route, and for you to access it, just put in the number, and then you'll be able, to access wherever you want to be. So after the default gateway receives a communication request, it performs the routing forwarding to an initiator to, telling it that, I've received your packet and I'm going to be able, I know where that route is and I can reach to that destination. I know where I can get that person. I know where they are, so please send me your details and I'll forward them to you. The default gateway is a special routing mechanism, and it is usually the last choice of routing or route forwarding. Because remember now, in actual normal senses, when you send a packet and it's within the same network, it will be propagated. But once this packet, they have, cross-checked all the routing table or the forwarding table, and this particular record is not there, then they'll be like, you know what, I think this person is not part of our neighborhood. Let us go and ask this gateway or the borders and see if they know how best we can get to this guy. So it is the last choice of forwarding. It is the last choice of forwarding, and it means that the default gateway is used for forwarding packets when no routing entry is available in our routing table. All right, so let us look at a virtual local area network, what we are calling the VLAN. The virtual local area network is the most common way to subdivide a physical local area network into a separate logical broadcast domains. You're just basically getting, it's one physical network, but you're going to logically divide it into logical different broadcast domains. In that, devices within the same VLAN can communicate with each other using their MAC addresses, which those in the different VLANs cannot. Like if this guy is in VLAN 1, can only communicate and send broadcast packets to this virtual machine 2 here, which is also in VLAN 1. Only VLAN 2 can be able to communicate to VLAN 2. And should it want to communicate to VLAN 1, means then it has to do some kind of routing, and means it has to go through some kind of layer 3 routing for it to be able to access the packets within within virtual area network 2. So this is done to help you. Let's say you have a department and you say this VLAN 1 will be for HR department. This VLAN 2 will be for, finance. This one will be for, let's say, logistics and etc. So you're going to subdivide your physical network into some kind of logical divisions, and broadcast packets can be propagated only within a VLAN and cannot cross VLANs. That is the entire logic. The benefit of this is that it helps us to harden our local area network security. Because packets from different VLANs are separately transmitted, hosts in one VLAN cannot communicate with hosts in another, without using IP addresses. So if they want to communicate with hosts in another, they have to actually use routing, and they use IP addresses. It also helps us to improve on network robustness. How does that happen? It's that if a fault in one VLAN, this one of HL goes off, it's not going to affect other hosts in other VLANs, okay? Because these guys are now logically subdivided. There's also flexibility in terms of defining virtual work groups, and also these work groups can obtain users from different, geolocations, and this allows flexible networking and makes even maintenance a bit easier. Okay, so usually in a VLAN, kind of networking, the packet is added with a 4-byte, a 4-byte length header, and it's usually tagged. It is usually a tagged, packet. It is tagged with that VLAN ID for us to be able to identify that this is a tagged ID of a packet from VLAN, and it is supposed to be going to this VLAN. So we have two kinds of packets. We have a packet Ethernet frames, which is tagged, and we also have a Ethernet. Let me write it here, and one which is untagged. So we have one which is tagged, and we also have one which is untagged. So although also operating systems and switches are both able to add VLAN tag to our data frames, VLAN tags are usually added or removed by switches under normal circumstances. These guys are the ones responsible for processing those kinds of tags. And here we have these kinds of links. As you can see, we have our trunk, and we also have what we are calling access links. And I want us also to draw ourselves attention to what or how these kinds of links differ. So the access link, this link from here to there, is what we're calling an access link. As you can see, it is going to connect our host to a switch. Okay, it's going to connect our host here to a switch. It is what we call the access link. And generally, the host does not even need to know which VLAN it belongs to. And the host hardware, even this network interface card, it does not even try to understand or cannot even identify the VLAN tags frames. Therefore, the host only receives or sends untagged frames. Please pay attention to that. Our hosts here, it's only going to receive or send untagged frames, because for it cannot even process the VLAN IDs. It doesn't even care. It's not even concerned. So it's going to only receive or send untagged frames. So we also have another link here, and it is what we are calling a trunk link. And the trunk link here helps us to connect a switch to another switch or to a router. It can connect to a switch or it can be connecting to a router. And data of different VLANs is transmitted along this trunk link. It only transmits data of different VLANs. Therefore, the two ends of a trunk link must be able to distinguish frames with different VLAN tags. This means that only tagged frames are transmitted along trunk lines. Only tagged frames are transmitted along trunk lines. Okay, that is the difference. Access link, they connect switch to the host. Trunk, switch to switch or switch to router. Now we also have different interfaces, and I want you to draw attention to this. We have these interfaces that are going to be connecting these things. The interfaces, where are these guys connect? Are you seeing those interfaces? We have those interfaces. So we have one, what we're calling the access interface. The access interface here, these access interfaces reside on a switch. This switch you are seeing here, but not this side, because now the side is connecting. This switch you are seeing here, this is also an access interface. This is an access interface. This is an access interface. This is an access interface. Also, that is an access interface. So the access interfaces reside on a switch, and they are used to connect the interface they're used to connect to the interface of the host. That is, the access interface can only connect the access link. Remember, we talked about the access link. This is our access link. Therefore, the access interface here can only connect the access links. I hope that has been driven home. And only packets carrying the default VLAN ID of this interface can pass through. Also, Ethernet frames sent through an access interface do not need to carry any tag. So if you are sending it to the host, remember, when it comes here, it will be stripped off and it will be untagged and it will be sent to the host. Or maybe when the host is sending out a packet through the access link, it is automatically tagged with a default VLAN ID, and only the default VLAN ID tag will be sent through the access link. That is what we are calling the access link. Let us also look at what we are calling the trunk interface. So the trunk interface, this is our trunk interface. As you can see already, it connects trunks. A trunk interface is to connect a switch to a switch or to a router, and can connect only a trunk link. We already talked about this trunk link, and can connect only a trunk link. And a trunk interface permits the tagged frames of multiple VLANs to pass through. Only tagged frames. So if it comes and it's not permitted, it will definitely be discarded. And we're going to look at that, I think, in the next few coming slides. So we looked at broadcasts. We have looked at routing is basically finding the optimal route. How am I going to reach host B? How am I going to reach host A? And how am I going to reach host C, which is in a different segment? So it's going to choose the optimal route using a layer 3 device, which could either be a layer 3 switch or a router, and then it will be able to send the packets to that. The default gateway I've also explained, and also when it comes to the VLAN, I have also explained. So let's try and look at the physical architecture of the network device. But before we go to the physical architecture, I just want us to draw our attention to this and also see this. So we have our access interface, right? We have talked about the access interface. So I want to explain what happens when someone is sending or when it is receiving a untagged frame, the access interface, right? One, it is receiving untagged frame. What is this going to do? When it is receiving an untagged packet, it is going to receive the packet and tag it with a default ID. Host here is going to send the packet, IP packet, and it's going to send it to our interface, our access interface. When it is receiving it, it's going to receive it, and then it's going to tag it. It's going to add the default VLAN ID. The default VLAN ID is the VLAN for this particular segment. Okay, so it's going to receive it, and then it's going to tag it with a default VLAN ID. What happens when it is receiving a tagged frame? We have been looking at the untagged. Now, what happens when it's receiving a tagged frame? When it is receiving a tagged frame, if the VLAN ID of the packet is the same as the PVID, the PVID is the port virtual ID, and and it's the same as the PVID of the interface, then it will receive the packet. Otherwise, it will discard it. Remember, we said that it's going to, this guy only transfers tagged frames. So let's say this guy here, B, is sending a packet to A, and they are within the same VLAN ID, right? They're within the same VLAN ID. And it's going to send the packet, it's come through that trunk. And remember, the trunk said, moves that tagged frames, and it's going to come to this interface, and it is receiving it and is tagged. It's going to be like, oh, okay, it's within the same VLAN ID. Okay, then okay, I have seen it. Then I have to receive it. Then it will receive it and send it and forward it to packet A. Okay, it will receive it. And if it is not within the same VLAN ID, this VLAN 1, and that ID is not 1, then it will go ahead and it will discard the packet. It will say, no, I am in VLAN ID 1, and I don't know, maybe this VLAN is coming from 2 or 3. I'm not supposed to receive it. Then it will not go ahead and it will not receive it. So when after receiving and it is sending, what will happen? It will strip off the PVID tag from the frame and then send it. Remember, it's an access interface and it is sending to the access link. And we said access link carry untagged frame. So when it receives it, then the next thing is to send. As it is sending, it's going to strip off the PVI and then it will send it to the host. This is the access interface. I hope that is clear. Summary: when the tag comes and it is untagged, meaning most likely it is coming from the host and it is going in like this guy is sending, and it is untagged because hosts, remember, send untagged frames, and it comes into our network interface here and it is untagged. What it's going to do, it's going to receive the packet and it's going to tag it with a default VLAN ID because it's coming from the host, and this host is in VLAN ID 1. So it's going to tag it with a default VLAN ID of 1, right? And then it's going to send it through the trunk. The trunk, of course, you're going to also look at it. And then the trunk will send it all the way to this interface. Now, when this interface receives, now remember it has been tagged, right? Our ID is 1. It has been a tagged frame. So when this interface now receives a tagged packet, what is it going to do? When it receives a tagged packet, it's going to look and see, is this the same as my VLAN 1? And if it's the same as VLAN 1, it's going to receive the packet. If it is having ID 2 or 3 or whatever, it's going to discard the packet. After receiving the packet, then it will send the frame. But before sending the frame, it's going to remove the ID, because remember, hosts, we said, and also under our access link, we only transfer untagged frames. So it will go ahead and strip off the tag from the frame, and then it will send the frame to the host. Now let us look at the trunk interface. We have been looking at the access interface. Now let us look at the trunk interface. So if it's receiving a packet that is not tagged, right? If it is receiving a packet that is not tagged, it is going to tag the packet with a default VLAN ID. And if that default VLAN ID is allowed on the interface, it will go ahead and receive the packet and tag the packet. Sorry, I'm saying that it's going to tag the packet with a default VLAN ID, and if the default VLAN ID is allowed on the interface, then it will receive the packet. Let's say it's on this trunk and it receives untagged packet. Let's say it's coming from whatever. It's going to go ahead and check through the default ID. Let's say it's 1, and it's going to tag it with the default VLAN ID. And if default VLAN ID that you configured is allowed, because you go on this trunk as a network engineer and say permit this permit this ID 1, 2, 3. So if it is allowed and permitted to go through this, then it will go ahead and receive it. But in case that it's going to tag the packet with a default VLAN ID, and if the default VLAN is not allowed, then definitely it will discard it, because the default VLAN is not allowed to run on the trunk. What happens when it's getting a tagged frame? This was when it's untagged. Now, what happens when it's getting a tagged frame? When it's receiving a tagged packet, the VLAN ID is allowed on the interface, then receive the packet. It's going to look at your ID. What is your ID? It is 1. Is it allowed to go through my trunk? Yes. Then receive it, right? And if the VLAN ID is not allowed, then definitely you know what it will do. It will not receive it. It will discard the packet. And when it comes to sending, now we have looked at it. It has looked at it, either received it or discarded it. Now, if it has received it and it wants to send it, in the process of sending, if the VLAN ID is the same as the default VLAN ID and it is allowed on the interface, then it's going to just untag and then send the packet. Okay, it's going to untag it and then it's going to go ahead and send the packet. And if the default VLAN ID is different from the default VLAN ID and it's not permitted, then it's going to and it's permitted, it's going to keep it unchanged and then it will send it. Because if it's a default one, we know we are moving it on that network. So just go ahead and untag and then send it because it's on our default VLAN ID. But it's not the default one. Let's say it's 3, but it's permitted. Just receive it and then go ahead and process it and maybe send it to the desired VLAN. That is all about VLANs. Let us look at the physical network for virtualization. We have been looking at these things. We've been talking about them. We have been mentioning them. But now I'll give an opportunity to some of you to go ahead and tell me. I think we have talked more about the router. We have also talked about switches. We have also talked about layer 3 switches, server. This is just basically a physical network interface card. It's the one on the physical machine, even your computers, where you put your Ethernet cables and you fix it in, I don't know if I can draw it very well, and you fix in your network cable, and then you are able to connect it to either your switch or to the router. So this is the network interface card. Usually most of them come burnt with a MAC address. And layer 3 switch, it has the routing capabilities, and also the router is also a layer 3 device which also has a routing capabilities. So a router in a virtualized environment. What is the role of a router in a virtualized environment? We already said that a router as any traffic that is going to traverse a router is which kind of traffic? Who remembers? North-south traffic. Thank you. North-south traffic. So that is a router in a virtualized environment. Now, a switch in a virtualized environment, when we have our physical switches and what they are used to do, because remember, these are physical servers with physical network interface cards. So the kind of traffic even that is generated from these machines is somehow different. Let's say you have created your physical server, and this is the physical server is what you're going to use to actually access, let's say, you're going to access and maybe configure some virtual machines here. The traffic that is going to be generated is what we're calling management traffic. The traffic that is going to change the configuration commands, etc, etc, etc. Let's say these virtual machines are going to access the storage media. They're going to access and do some kind of services and access some kind of services on our server. Then the kind of traffic that is generated is what we're calling service traffic. If our virtual machines are going to access storage, or even you as yourself, you're going to access some files on our storage, devices, then the traffic that is going to be generated is what we're calling storage traffic. If you also want to manage the services, stop some of the services, start some of the services, go there, stop this, open this, then the kind of traffic that is going to be generated is either management and service traffic. layer 2 switches in a virtualized environment. We can have our layer 2 switches, and we can choose to, depending on how you want to develop and organize your architecture. We have our management switch, we have our storage switch, which is connecting to our storage devices, and we also have our service switch, as you can see. So we have our physical servers here, we have our storage, storage devices, we have our users. So if at the same time the users access, the management switch to go ahead, if they want to, to access storage, they'll have to go, through that and this, and then they're able to access some of those devices. So basically you can just connect your architecture that way. But as you can see with the layer 3 switch, you just need one, intelligent, powerful switch to be able to take care and manage your traffic and divide it accordingly. Whereas with layer 2 switches, you may need to have to set them up separately and differently. When it comes to the physical, when it comes to the physical NICs, the network interface cards on your machine, then you can either have them in 2 modes. You can have it one, or you can choose to bundle them. When you bundle them and you form some kind of logical form, which now you can also use to divide your traffic accordingly. How do we bundle that? We can use some protocol that they call LCP. Who has heard of LCP?
Link aggregation control protocol.
It is link aggregation control protocol. Thank you. So a physical server, any machine, all our computers have its own physical network interface card, which is used to connect to the internet or to the network. And all virtual machine traffic enters the entire network through that kind of physical network interface card. That's why the physical network interface card involves a key concept, which is port link aggregation. Because if it's just one, and imagine all that traffic is going through that one network interface card, then there would be a problem. So with the port link aggregation, or the port aggregation, indicates that multiple Ethernet links can be bundled into one logical link. Like you can see this link, which is bundled together, can be bundled into one logical link to increase the link bandwidth. And the bundled links can be dynamically act as backup to each other, thus improving on efficiency and also improving on reliability. Okay, so we can use protocols like link aggregation control protocol, which allows multiple ports to be put together into a logical port to increase the link bandwidth without necessarily having to upgrade our hardware. We can use this kind of mechanism also to offer a backup mechanism, also enabling us to have high reliability. The purposes of using such tools, it helps us to increase our bandwidth, and also it helps us to have higher availability, and also we can do load balancing through using this kind of protocol. We can use this protocol in both manual and also in an automated mode. In manual load balancing mode, the user must manually create the links and add their members into that bundled link. In automatic, you can just set policies, and when that kind of policies is reached, then automatically, or the different devices can now automatically form an aggregated link and start the link to send and receive data according to its own configurations. But there are 2 ways you can use the ALCP. Now let us look at network architecture, or the virtual network for virtualization. And we want to look at this mainstream architecture and try to understand how some of these things work in a virtualized environment. So I want to look at the mainstream virtual network architecture and try to understand what it is. So as cloud computing and virtualization increasingly becoming popular, in our traditionally, IT staffs, usually divided things like, this is a network engineer, this is a systems engineer, this is a software engineer, and all of them had clear-cut instructions, right? That for me, I am dealing with a network. For me, applications, I'm dealing with application. But now in a cloud environment or a virtualized environment, things are becoming a bit complicated because guess what? Virtual switches run inside servers. These servers are meant to be taken care of by a system engineer. But now it is some kind of software that is running inside a server. So when that fault occurs in an environment, it is not easy to determine who is to troubleshoot. Is it a network engineer or is it the security engineer? So the network engineer or the host engineer, so you don't know. So it is therefore necessary for you as a network engineer, for you as a security engineer, or even a cloud engineer and host engineers to acquaint yourself with the necessary architecture of a virtual network and how it operates. A common virtualization system uses architecture like you see in this architecture. We have our virtual machine A, we have a virtual machine A, we have a virtual machine B, we have also our virtual machine B. In a personal small scale virtualization system, virtual machines are bound to physical network interface cards using either a bridged mode or using a NAT mode, network address translation. Whereas in a large scale corporations, usually like those people like Amazon, those people who really, rely on virtualization systems, virtual machines are only connected to physical networks using things that they're calling virtual switches, which we talked about earlier on. And we're going to look at them later on, like this guy here, what we're calling a virtual switch. So network bridge here is not a new technology, and you can use network bridges to enable network ports to communicate with each other. And, you have yourself a successful, communication taking place. And we have NAT. In a NAT way, you actually have some kind of address translation done, and then you are able to effectively have communication. The network bridge also helps us. It has the advantage of learning learning MAC address learning. It learns the MAC addresses. It initially, because when you have just created and powered up the virtual machine, it has no mapping between MAC addresses and ports and sends data like a hub. But after sending the first, few frames and after receiving other packets, then it is able to learn and update its CAM table. Now, also, it does port forwarding or packet forwarding. And when sending each data packet, the network bridge obtains, the destination MAC address, and then it is able to send the packet to its intended MAC address. In virtualization also, each virtual machine, these virtual machines you are seeing here, they have all virtual network interface cards. These are virtual network interface cards, like the physical network cards you would have on a physical machine. Also, these guys also have virtual network interface cards. And a Linux operating system, if you're using Linux operating system, usually they come up with some kind of a tap device which operates at user mode. But every a virtual machine has what we are calling a virtual network interface card. And as you can see, we can either have one virtual machine can either have one or more virtual machine, virtual network interface card. So when the bridge mode here is used, the network bridge functions as a switch, right? And the virtual NIC is connected to that port of a switch. So it just, whatever IP address of this virtual machine will be the IP address that you will actually see on your real network. There will not be any kind of addressing. It just works as a machine when you have as a switch when you have used the bridge mode. And if you use NAT here, what NAT does, it brings the network bridge functions as a router, and the virtual machine is connected to a port of a router, and that's why you do some kind of network address translation. And we are going to see, we are going to talk about it a bit later on in detail. Okay. All right. So NAT, like I've told you, it is used for network address translation. And with NAT used for network address translation, a virtual machine can communicate with external networks through a NAT gateway. And we shall look at NAT gateway later on. The advantages of NAT you can already know that when an IP address range of a physical network bridge has insufficient available IP addresses, new IP addresses ranges can be added. Here we can have our private, inside our physical machine, we can have our private range of IP addresses, and they are translated, and we don't have to exhaust all our IP addresses on our network. They'll be translated, and whenever packets come back, they're also translated back to that machine. That is also one of the advantage. Okay, also it helps you if you're using NAT, the source IP can be concealed. The people on the other network cannot be able to determine exactly, because the address is translated, what is the exact IP address of our source virtual machine. And also NAT helps us as far as load balancing is concerned, to provide redirecting function. That is some of the advantages that we are using. But we are saying the bridge and NAT are used on a small scale, or even a personal level or small scale systems, because when the bridge is used, the statuses of virtual machine cannot be viewed, and traffic monitoring becomes hard or becomes impossible. That's why in big organizations, they decide to use more powerful tools, like what they are calling a virtual switch. Okay, in a large scale system, the virtual switch is used for virtual machines to communicate with external networks. And the virtual switch, just like you hear the word virtual, it is virtual, but it has all the functions of a layer 2 switch. And the virtual switch acts as an upgraded network bridge, removing defects of a network bridge. Currently, today, each vendor, right? Each virtualization vendor has its own virtual, switching products. For example, when it comes to VMware, it uses vSwitch. It calls its switch vSwitch. Cisco calls its switch Cisco Nexus 1000V. And then Huawei calls its Huawei DVS. So all different vendors, even Lynx has Lynx, it's called Lynx DVS. They also call it DVS. And also other, vendors have different, virtual switches that they use. And all of them, most of them, they use, some operating system. Remember, like we said, VRP is used to manage all Huawei operating system. Also, these virtual switches have some kind of operating system, but most of them use what they call open source vSwitch, which is an open switch operating system for virtual switches. So the open vSwitch, or the OVS, is an open, is an open source, high quality and multi-protocol virtual switch, and it was developed by Nicira Networks using the open source license protocol. It is designed to enable massive network automation through programmatic extension, and also support network integration. Now, sorry about that. So why the obvious was developed, but before we go to the obvious, I just want to take you back to this picture here and show you these different modes that we have talked about. We have said either virtual machine here, one, can communicate and access our external network from our physical server through either bridged mode and connect directly. It works in a switch mode and connects directly to our network interface card. We have another way here where it can use the NAT mode, and there's some kind of network address translation, and it works as a router. It can connect directly to our network interface card. We say there's also another way here where our virtual machine 2 and virtual machine 3, they can connect to our virtual switch. We have some kind of virtual switch inside our physical server, and we have said they use some kind of operating system called OVS. And this virtual switch is going to connect them, give them different ports or interfaces, and then they will connect them. And you can see here we're using some kind of protocol to bound these two, interfaces together, interface 1 and interface 2, so that we increase on our bandwidth and also that we increase on our reliability and also perform some kind of load balancing and redundancy. So which kind of protocol? I talked about it. Which kind of protocol did I say we can use to bound, two links together, two network interface cards together?
Link aggregation.
Thank you. We said we can use link aggregation control protocol to help us bound those links together. Very good. So we're talking about the OVS. We already went through the bridged mode, where if you're using Linux operating system, there's some kind of tap mode. If you can see the notification, it goes through the tap. And as you can see, the header packet is not changed whatsoever. It works in a bridged mode, just like a switch. The packet goes through and it is sent and received the way it was sent. When it comes to the tap mode, to the NAT mode, as you can see, our address as it goes through the tap, our packets are, they change. Are you seeing? Our packets header are changed and translated as they go through the bridge mode, and then they are translated. Now we're looking at the virtual switch, or what we're calling the Open V switch. We said it's an open source virtual operating system for our virtual switches, and it helps us to achieve some of these benefits. It's secure, it can perform quality of service, traffic queuing, and traffic shaping. There is monitoring. You can use NetFlow, SFlow, Span, or Rapid Span to effectively manage and monitor your network. There's also automated control through using tools like OpenFlow, OVSDB management protocol. So there's also something that they call a distributed virtual switch. Like you hear the word distributed virtual switch. Previously, we have said that the virtual switch can be a common virtual switch or a distributed virtual switch. A common virtual switch runs only on one physical machine, just like you have seen in this illustration. This is one physical machine here, right? And one virtual switch runs only on one physical single host. So all network configurations apply to only to virtual machines on that physical host. Whereas distributed virtual switches are deployed on different physical hosts. And you can use virtualization management tools to configure the virtual switches in a unified manner. And the distributed virtual switch is required for VM virtual machine live migration. Huawei also uses all its products use distributed virtual switches. And this section, we also want to learn more about Huawei's distributed virtual switches. So a distributed, like you hear the word distributed, is distributed across different machines. We have machine 1, we have machine 2, and we have machine 3. So we have our virtual machine. This is virtual machine 1. It's in a different machine. This is also virtual machine 2. This is also virtual machine 3. And all these guys are in different physical machines, but they're all using one distributed virtual switch, and which is supported by our OVS, the Open System Virtual Switch operating system. So let us look at the next, the architecture of. Let us look at the architecture of Fusion Compute Virtual Architecture. But before we do that, I just want to say that Huawei distributed virtual switches can be centrally managed, and the centralized management module provides a unified portal for simplified configuration management and user management. Virtual switches distribute on a physical server, provide virtual machines with a range of capabilities where you can do those things which I talked about here, the advantages of security, quality of service, monitoring, and automated control. Just to take note out of this, for the sake of multi-choice and single choice, I want to mention that multi-distributed virtual switches can be configured, and each distributed virtual switch can serve multiple physical hosts or CNA nodes. in a cluster. CNAs are just like physical computers, like nodes in a cluster. So you can have one serving multiple. You can have one distributed switch, like you see this guy serving multiple CNAs in a cluster. This is CNA1, CNA2, CNA3, or different physical hosts depending on the name you want to use. Or you can even configure and have multiple. You have another one inside here, depending on your need and what you want to achieve as a network engineer or a cloud engineer. And a DVS provides several virtual switch ports, which we are calling the VSP, virtual switch ports, and with the configurable attributes such as the rate and statistics. And all the ports with the same attributes are assigned to the same port group for easy management. And ports that belong to the same port group are assigned the same VLAN. Please take note of that. All the ports that belong to the same group are assigned to the same VLAN. I hope you have taken note of that. So different physical ports can be configured for other things like the management plane, storage plane, service plane, etc. We also have what they call the uplink. And an uplink port is basically, sometimes they call it an uplink port aggregation group, and it can be configured for each DVS to enable external communication of virtual machines served by DVS. So an uplink is this link from, actually this picture would best illustrate it. An uplink is this link from the switch to our physical network interface card. So the link from the switch to our physical interface card is what we are calling the uplink. Okay, I come back there and I can say also that, yeah, basically the uplink, I think that is all I wanted to say. A port group, I've been talking about port groups. I said ports of the same group must be assigned to the same VLAN ID, and a port group can consist of multiple ports with the same attributes. So if you configure the port group attributes, including the bandwidth, the security attributes, and the VLAN, the administrator here, it is easy for him to manage and configure the attributes of all virtual machines by just changing the attributes of that port group, thus saving a lot of time. Though port group attributes changes do not affect only the virtual machines that are already running, but all other machines will be affected. But the virtual machines that are running, the changes do not affect them. I hope you have also taken note of that. Like I said, an uplink connects the host and the DVS. It connects the physical network interface to our distributed from our DVS to our physical network interface card. So Huawei also supports the virtual switching function, and it also uses the open vSwitch technology like we have earlier on discussed. So we want to look at the Fusion Sphere architecture. But before we do that, let us also look at the traffic flow of how traffic is going to flow from one port group to another. So we have these virtual machine. Let me name them. This is virtual machine A, this is virtual machine B, this is virtual machine C, this is virtual machine D, E, and F. And we have two physical hosts. This is physical host 1, this is physical host 2. Remember we said they have different port groups and they have different VLAN groups. In my earlier discussion, I told you that only virtual machines within the same VLAN can communicate and send broadcast packets, minus having to involve some kind of routing, right? So they can only communicate to those peers in the same VLAN ID. And usually the VLAN IDs are also configured with the port groups, which are always the same as the VLAN groups. So we have these guys. So we have virtual machine A, and according to this configuration, he was put on the port group of VLAN 100. We have virtual machine B, and he has his port group is VLAN 200. And we have virtual machine B still. It has two network interface card. It has one interface card 1. It has a second network interface card. And the second interface card is configured to be connected to port group 300. And also our virtual machine C, which is also running Linux installed on it. It has its one network interface card, and it is connected to port group 300. Our virtual machine D here, like you can see in the illustration, it is connected to port group 300, and virtual machine 200, virtual machine E is connected to port group 200, and virtual machine E is communicated to port group 300. So quick question, in your understanding, if virtual machine A wants to communicate with virtual machine B here, do you think virtual machine A will be able to send packets from this machine to that machine minus going through a layer 3 device to route its packets? Anyone?
I
Yeah,
won't be able to.
Yes, please. Mic check and you speak.
mic check.
Yes, please.
So it would have to go through a layer 3 device because they're in different VLANs.
Because they are in different VLANs.
Mic check.
I think he has said it, so that is okay. Very good. So that means that much as they're within, it is within the same physical host, isn't it? For this guy to be able to communicate with B, his packets have to go through our uplink. Remember the uplink I told you, which connects our switch to our physical network interface card. Go through our uplink, go through our layer 3 switch, let's say, and then it is able to send the packets, and then this layer 3 switch will perform the routing, and then they come back, because now this knows, it has probably the default gateway, and now knows that these packets are meant to go to virtual machine B. Another question, do you think virtual machine B will be able to communicate to virtual machine C minus needing some kind of routing, IP routing? This guy wants to communicate with that guy. Do you think he'll be able to?
Yes, he can.
Yes, he can. Why?
Because they are sharing the same VLAN.
Mic check.
Yes, please.
Mic check.
Yes,
they can communicate. Yes, they can communicate because they are in the same VLAN.
Very good. Because this guy's network interface card is within the same VLAN. So definitely they can be able to communicate and send packages with each other. They don't even have to go through the physical device here. Okay. But we have also another scenario here that I want you to pay attention to. We have another scenario here. As we can see, virtual machine A here is in VLAN 100. And also virtual machine F is in VLAN 100. They're the same VLAN. They don't have to, route their packets, right? They just need to send because it's in the same broadcast domain. So they just need, to send their MAC addresses, and they're able to communicate. Virtual machine F. But this is physical host 1. This is physical host 2. Do you think, and they have a distributed virtual switch, do you think for host A to be able to communicate, for virtual machine A to be able to communicate with virtual machine F, will have to go through the physical device?
Yes. I don't think that A would have to go through a physical device, because the distributed virtual switch does that. And since A and F are in the same port group VLAN 100, then
Thank you for sharing, but I want to draw something to you. This guy here, it is virtual. It is not tangible. It in fact here, just think of it doesn't exist, but it's virtual. They're just showing you that it is spanning across different hosts. Think of it that even this one physical host, this physical server 1 is one room on the first floor, right? And this one is on the next block at the corner of your campus on 3rd floor, much as they're using the same distributed virtual switch. I'll pose that question again to you. Do you think they'll have to go through a physical device to communicate?
Mic check.
Yes, yes,
Yes,
Prosper.
I think they would need to do that. They would need to do that since I'm sure the distributed switch will be configured on both the floors. If you're giving that example of floors to act as one, but physically they need to go through some physical device for them to actually be able to communicate via some sort of uplink.
Thank you, thank you. That is it. Because yes, much as they're the same VLAN and same port group, but remember these are physical machines, right? Remember these are physical machines. They are somewhere in your room, and this one is also somewhere here. For physical machines to even be able to send packets, regardless of whatever packet there is, you need some kind of medium, isn't it? How are they going to communicate if there's no physical connection connecting them? There's even no Wi-Fi connecting them. How are they going to be able to communicate? You get that picture. So these computers will be connected somewhere to a physical device, which will enable them to communicate. The only difference here is that these packets that are going to be sent from virtual machine A to virtual machine B will not be routed, because the same broadcast domain, much as it will go through here, they will just be forwarded to this broadcast domain. They will not be routed. Okay, I hope that makes sense. So let me just run the illustration for you to be able to understand some of this traffic flow. So we have our machines here, and as you can see, for this virtual machine to be able to communicate with virtual machine A, it by all odds has to go through layer 3 routing, and it has to go through our physical device. Much as they are within our same physical machine, it will have to go through this device, this switch, for it to be able to reach our virtual machine here. But this guy, when he wants to send packets to this guy, they're the same VLAN within the same machine, and they have their distributed virtual switch. So he will just go ahead and send the packets, and this person will receive the packets happily. But if this guy now wants to send packets to this guy, much as within the same VLAN, because there's actually, think of this, much as you're seeing the illustration, but they could even be in totally 2 different rooms, or in totally 2 different locations even. Okay, so this guy will have to go through your physical network architecture to actually be able to communicate with this guy. So that is how that works. So we want also to lastly look at what you're calling security groups. And you can, as you hear the word security group, it is basically what you're calling security group. So users in computing or virtualization, users can create security groups based on the virtual machine security requirements, depending on what you want to achieve. This is my database, this is my DB server, and my DB server, I need to make sure on the only packets that are sent to it, FTP packets. I don't want any SSH packets. I don't want any ping packets. I don't want whatever you may want, depending on what you need is. So you can configure security. You can configure security groups based on your requirements as an engineer, and each group provides a set of access rules, right? You have a set of access rule 1, rule 2, rule 3, etc, etc. And VMs that are added to a security group are protected by the access rules of that security group. So if this security group is A1 and I add this virtual machine, this is my application server, let's say, and I add it on this security group and this, so all these security groups, all these virtual machines will be protected by this security group. And I can go ahead and just edit the security group, and all the virtual machines inside there are also affected accordingly. So users can add virtual machines to security groups for security isolation and also access control when creating virtual machines. And a security group is a logical group that consists of instances that have all the same security protection requirements, and they trust each other in the same region. So all virtual machine NICs in a security groups communicate with each other by complying with these group rules. Like, let's say we have this forum, this class here, and we have set our rules, and we're saying if you want to talk, you unmute and talk. After talking, you go ahead and mute yourself. And if you have a noisy background, kindly don't talk. So everyone who is in this meeting has to comply with these group rules, which we have been able to put up and the groups which I have set up. Okay, and that's why if someone is not complying, then they're not permitted. And if something is coming up and it's not part of this, then it is not permitted. Also to note, a virtual machine network interface card can be added to only one security group. Please take note that its virtual NIC can only be added to one security group. That is also very important. So the security group performs or provides similar functions as the firewall. They use IP tables to filter packets for access control, basically. Okay, so just like you can see, just to demonstrate, you set your packets and say if virtual machine A is sending packet A and complies with that rule, permit it. And if also complies with that rule, permit it. And if it doesn't meet, if also complies with that rule, also go ahead and permit it. Then our database application server will go ahead and receive it. And if another packet is sent by packet B and it complies, permit it. And if it doesn't comply, then go ahead and discard it. And then our database server will not access or will not receive the packet. So this brings us to the quiz. And I want to ask, which of the following falls into the category of north-south traffic? Which of the following
Mike,
falls
check.
into the
Can you
category
Traffic
check?
generated when user access the data center through the internet.
Okay. Please say mic check, and also when you're giving the answer, explain to
Mic
us
check.
and tell us why. Yes, Danish.
Can you take us to the pool?
You
So
want
that
the
we can get
poll?
us. Yeah. Take
Okay, let
this.
me disable the answers here. Let me disable the chat. Boom, chats are disabled. Let me create the poll. Just give me a few seconds. Few seconds. Polls it is, polls it is, polls it is. I've not seen that you want polls, so I'll make sure that I prepare them promptly.
And Sandy, just to contribute on the same, every
Yes.
time when you reach to the quiz part, can we ensure that you do the polls and not this confusion that we experience by people having this talking about different answers and things like that?
Okay, you want the polls? That is taken note of. I'll make sure that I prepare them on time.
Yes, I think that will work out and help us to avoid this confusion.
Okay, no problem. Working on it. Okay, I have a problem. This is not going to be complete, but you will just bear with me. The poll does not support multiple, very long questions, but you just bear with. Actually, let me find a solution for that. Just hold up. Let me first pause the recording. Okay. This chapter covers basic knowledge about, we have looked at the basic knowledge about physical and virtual networks used in virtualization environment. And you can go ahead and look out for this material for further reading. And I'm also going to share some on the channel tonight without fail. And thank you for being part of the lecture, and thank you for being interactive and also interesting.
Sandy,